In our paper, I'd like to describe how one can use neutron scattering to determine the structure of silica gels and also determine the properties of water in the pores within silica gels. So we'll be talking about the intermolecular structure of water and the dynamics of the water molecules. This paper then has very close links with Peter Hall's talk already this afternoon, and also has links with the paper by Dr. Adkins this morning, who talked about packings of spherical silica particles. In many respects, the structures we'll be considering are made up of packings of uniform spherical silica particles in going from a sol to a gel. So we have the first slide. There are two techniques we'll be covering. Peter has already mentioned these. The first, is that focus? Is it? Good. The first will be concerned with the ways we can use small angle neutron scattering to follow the structure in a concentrated silica sol as we remove the water and produce a porous gel. And we'll show that this process gives rise to a uniform type of structure which we can determine from small angle scattering, and using that type of structure we can go on to use inelastic and quasi-elastic neutron scattering to probe the properties of water in pores with different geometry. So you might ask, why do we do this type of work? Well, I think we're interested in the range of perturbation of the silica surface on the water structure. Water saturating pores will be hydrogen bonded. It will have a long range structure, and one will be interested in the extent to which the surface can modify that structure. So we're interested in the hydrogen bonding, and to do that type of study, really one needs to have a well-defined pore structure to start with to draw any definite conclusions. And perhaps we could also say that if we knew something about the correlation between porous structure and properties, say, of water within pores, particularly small pores, it might enable us then to have a non-destructive means of looking at hydrated porous materials like cements, and from that type of study of the water, one could learn about the porosity in more ill-defined systems. And I'll say something in particular about the properties of water in the supercooled region. This is a region which is attracting a lot of attention now because one has anomalous properties and extensive hydrogen bonding in that temperature range. Now, if we want to produce uniform structures, porous structures, we could study gels composed of spherical particles. We'll be considering spherical particles of different diameter. We can vary the water saturation, and that will enable us to look at the effect of the surface at different distances from the surface. Alternatively, we can fix the particle size, vary the packing density, and other speakers have mentioned what one can do by compacting fine powders to different porosity. What we'll be concerned with is looking at fixed particle size and varying the packing density, if you like, in going from a sol to a gel. And just schematically, this just illustrates the type of interpore space where we would have with a cubic type packing of spherical particles. Here we have a tetrahedral packing, and you can see the extent of the surface may be less marked out further from the surface in this case than this case here, where we have a much more dense packed structure. Just to quickly recap, where we're doing neutron scattering, we have with thermal neutrons, we have a range of energies corresponding to different wavelengths, and because the neutron has a high mass, we can measure the velocity. This energy corresponds to a certain velocity. In general, we were talking about time of flight spectroscopy, where we measure the time of flight, the reciprocal velocity, and we can measure the energy change on scattering. We'll be considering coherent scattering, elastic scattering first, small angle neutron scattering, which Peter's mentioned, we'll be talking about this scattering vector. The inverse of that scattering vector is in this range here, which is in the colloid side range. The inverse is in the colloid side range, so we can probe properties of structure in that range of size. Schematically then, what we're doing is taking a sol, a silica sol, spherical particles, removing water, producing a gel. And we can follow that process using neutrons because the neutrons are transmitted through quite thick samples. We have no problems of absorption, and we can probe the changes which occur. And this is showing small angle neutron scattering results. Here we're measuring the intensity as a function of this scattering vector for different concentrations of silica sols. In the case of a dilute sol, we have a scattering from which we can determine the size of the particle. Here, as we go up in concentration, and the particles have a diameter here of 16 nanometers, we see these interference peaks, and that tells us we've got short-range ordering occurring in these systems. And from an analysis we won't go into, one can obtain information about the distance between, the average distance between particles, and that's illustrated here from the radial distribution function. This is the probability of finding a pair of particles separated by a given distance r as we increase the concentration here. And this is the most probable separation distance for that concentration. And you'll see as we go up in concentration, the particles come closer together. And from that type of analysis, we can also obtain an insight into the coordination number, the number of particles surrounding a given particle in the system. And in that case, we find we have a coordination of between about 8 and 9 in the gel. We have a very densely packed system eventually. And that's illustrated here by nitrogen absorption isotherms, where we're looking at a range of different silica gels where the particle diameter is increasing. We've shifted the absorption axis here. We start off with 8 nanometer particles. These are 12, 16, 30, and 80 angstroms in diameter. You note that the surface area is decreasing as we go up in size of particle. The pore size is increasing, as you can see from the hysteresis loop. The important point to note, and we've just shifted the axis here, the important point to note is that the pore volumes of all these gels are very similar. They're around 0.2, 0.25 as shown here. And from these pore volumes we can calculate the porosities, and they're in the region of 0.3 up to about 0.35, which corresponds to an efficiently packed structure, and we think we have a random close, something which approximates to a random close packed structure. Now we'll just consider this gel here where the diameter of the particles is 16 nanometers, and we'll talk about the properties of water in that system. First of all, though, I'll just briefly mention supercooled water. There's a lot of interest now in the structure of supercooled water. Very good review by Angel, who describes a range of techniques to look at supercooled water. It's difficult to look at because it's metastable, and these are the various ways people have studied supercooled water in the past and more recently. Particularly we'll be concerned with the work of Texera at Sackplay, who's done quasi-elastic neutron scattering on supercooled water in capillaries, which one can cool the water down to -20 centigrade and still retain the liquid state. We'll be concerned with these porous silicas. So this is just illustrating what one has in the way of structure in ice, tetrahedral ice. We have 4 hydrogen bonds per molecule. This is a regular structure in ice, in bulk ice. In water, on the structure of water, on average, one has between about 2 and 3 hydrogen bonds, it's thought, per molecule, and it's a semi-ordered structure possibly. What we'll be concerned with is the transition from the bulk water, liquid, to ice. And as you can see, for that to occur, you've got to have an ordering of the hydrogen bonds in going to ice, and this transition may be affected by a perturbation of the surface. Now we turn to this inelastic, quasi-elastic scattering technique. Peter's already mentioned that the probe here, where we're looking at scattering from the protons, the hydrogen atoms, I should say, in the system, is we get very strong scattering because of the cross-section is dominated by this nucleus compared with the other nuclei one might find in the system. Peter was talking about energy changes down here, around 100 MeV, corresponding to these librational modes. We'll be concerned with other intermolecular modes at much lower energy, which one can find out about using time-of-flight spectroscopy, and we'll describe briefly results made at Grenoble on the iron 6 time-of-flight spectrometer. And we'll also show what type of changes occur in this quasi-elastic region due to the dynamics of the water molecules themselves. So we take two situations shown here and here where we have different silica contents, or the water content is decreasing and going from here to here, and this gives us, this is the mean interparticle separation between the particles. In the hydrated gel, where the particles are in contact, we have a value of 16 nanometers between the average distance is 60 nanometers between the particles centers. These are raw time-of-flight results for the silica gel containing the lowest water content at different temperatures. And here we're measuring effectively the scattered neutron intensity as a function of time of flight or energy. So this is this would correspond to the energy of the incident neutron. Neutrons on the sample. This is an energy gain spectrum we're measuring here, and we're going up in energy. This peak here would correspond to the librations. There are other modes here we're seeing, and you'll note that we're seeing quite marked changes as we go down in temperature. And in this condition here, we've got predominantly ice in the gel. And that's shown up perhaps a bit more clearly here. This is these quasi-elastic bands, the bands where we're measuring the broadening, if you like, of the energy of the scattered neutrons for the silica with the higher water content and lower water content, different temperatures. As we go down in temperature, these bands narrow up, and that corresponds to a slowing down of the motions of the water molecules. We can also extract other information here to show that even in this condition here, although most of the water is in the frozen state, then there is some residual liquid water there. I won't go into the detail of analysis, but one obtains these peaks at different Q values and makes model fits to a model. Well, the model we've used is that used by Texera, where we take a rotational and a translational motion, and these are results for the silica gel with the lower water content at different Q values. And these are results for the silica gel with a higher water content, this time at a lower temperature, and you can see these bands have narrowed up appreciably. And what one can do is make measurements of the half maximum, the function of Q squared, and these are typical results from which one can determine the translational diffusion constant. And these results are summarized here as a function of temperature for the translational diffusion constant and the rotational diffusion constant. This is the result that Texera finds for supercooled water here, and these are results for the temperatures we've measured for the gel containing the higher water content and the lower water content in the two situations. And you'll notice that for the higher water content, the translational diffusion constant around ambient temperatures is lower, and this is expected, and other people have found this. At the higher water content, then we have a behavior somewhat similar to that of supercooled water. In this situation here, we're determining the rotational diffusion constant, and you'll see that the behavior is very similar to that of supercooled water. And the point being here is that translations are much more affected by the perturbation of the surface and the hydrogen bonding in the structure. I think perhaps more importantly, the scattering in this inelastic region is in way more informative. Here we're measuring showing inelastic scattering then at lower energies to those that Peter was describing. I've plotted this in terms of milli-electron volts and wave numbers for different temperatures for this silica gel, which has got the higher silica content, the lower water content. This is the libration band. This is at a lower energy than found by Peter because he was looking at ice with a beryllium filter spectrometer. As we go down in temperature, this band shifts to higher energies, and here we've got predominantly ice. There's a marked change in the spectrum down here, and we're off the scale there. And this position of the libration is very sensitive to hydrogen bonding. The point to note, though, is that we see changes in this band here, which has been assigned to hindered translational motion. We also see, when we get ice, that we get this marked peak coming up here, which has been ascribed to a stretching mode of hydrogen bonds. And these assignments perhaps are a bit sensitive, but the point to note is that we're getting ice in this situation here. For the higher water content, these are results for 300 and 265 K. What we think we see here is evidence for, here we've got liquid water, obviously. In this case here at 265, we see this peak coming up. And I think what we see here is evidence for a mixture of liquid water and ice. And it would seem perhaps that the ice is forming further distance from the surface than the liquid water, which still remains close to the surface. And we've got this peak here, which shows us we've got liquid water still there. And we've done other work subsequent to this, where we have much smaller pores, where we've sorbed water into the pores and looked at the translational diffusion constants, and also looked at the inelastic region. In that case, we just see no formation of ice at all. So it seems that the pore space does determine whether or not one can form this long-range hydrogen bonded structure in ice. So we're concluding here. The main conclusions I've shown are that the in silica gels, the translational diffusion constant is much more markedly affected as we go down in temperature compared with the rotational diffusion constant, and that's because it's sensitive to the hydrogen bonding. We're looking at longer range movement of the water when we're looking at translations compared with rotations. We also see in the inelastic region that we get marked changes which can tell us something about the hydrogen bonding and formation of ice in porous media. At high water contents, we can get evidence of partial freezing, and I think we already can say that we're getting effects out to something like 20 angstroms from the surface, where we can see perturbation effect in this transition from liquid to ice. Thank you. Yeah, John Doyle's been interested for a long time in the diffraction of, I didn't talk about neutron diffraction, but his studies have been concerned with diffraction of water in porous silica, and that of course is a very important technique to apply if you want to look at these differences in structure. And he has indeed shown evidence that you get different types of ice in porous silica. He's looked at spherizol silica, which in many ways is made up in the same sort of way that I've talked about here. But I think he sees evidence for cubic ice, I think, Peter, doesn't he? As well as the structure of ice I showed there. There are considerable difficulties in using diffraction, I think, to look at the structure of ice, because you're measuring coherent scattering, and you've got all the problems of removing the background of the silica. So I would say that possibly looking at the inelastic modes at low energy could be more valuable. But you're right, yes, they have been looking at water, of course.
What is the feeling on the resonance of cubic ice, and I think maybe some alternative feeling was one from Robin Speedy, who said that perhaps there was some pentamer type arrangement.
I think we should,
Okay.
sure you can discuss.
Yeah.